Okay, thank you, everybody. I only have 15 minutes today, so I'm going to try to move pretty quickly. The title of my talk is Cutting Through the Hype, Real-World Applications of AI in Antibody Discovery and Engineering. So just a little bit of a background about Ailux. We're an 80-member team. We are the biologics division within XtalPi. We have over 10 years of AI-based drug discovery. We've worked with 15 out of the top 20 pharma companies, and we have over 50 AI models that we use. So today I'm just going to highlight a few of the AI models that we use for the sake of time. And then we also have the luxury of having a large wet lab space. So we utilize wet lab and dry lab in conjunction. So obviously AI is very hot right now. If you look at publications, the number of publications have been exploding, I think, over the past few years. And the question remains, is it all hype, or is there any bona fide impact? And I think today I'm going to try to show you how we utilize AI to get some impact in our antibody discovery campaigns. So today, no hype, just focusing on 2 case studies for the sake of time. We have a bunch of case studies that validate our platforms, and I would be happy to share any non-proprietary data with you if you reach out and we can meet after and talk. But today, just 2 case studies that validate our platforms. The first case study is a hit generation campaign, and then the second case study will focus more on engineering. So let's just jump right in. Case study 1 is an integrated discovery platform to identify diverse, functional, and developable antibodies. So we have a unifying antibody discovery platform. So we try to multiplex our projects and deal with multiple project goals at the same time. Obviously, for an antibody discovery platform, we care about epitope, affinity, and activity. But we also want to focus on developability at the earliest stage possible, and that's one of the ways that we use AI. And then we also want to focus on diversity of binders at the earliest stage possible, all the while keeping in mind time and cost. Now, there's no one-size-fits-all platform, right? So each of these platforms listed here have their own unique problems, and there's uncertainty, and it can be a lengthy process. So Ailux's solution is to integrate these platforms and run them in parallel. We do single B-cell screening, repertoire discovery on NGS, and then also phage display at the same time to identify hits in an effort to de-risk and accelerate the antibody discovery process. So for case study 1, this is kind of the meat of the presentation here, and I'm going to walk you through our AI-powered 3-in-1 antibody discovery platform. We can go from immunization to high-quality hit lead-like molecules in just 3 months. And I'll walk you through a little bit about how we use our AI platforms to do that. So this is a specific real case that we did where we took 2 immunized mice and we run it through our 3 platforms in parallel. Our single B-cell screening platform, Smart Fluidics, our repertoire discovery platform that uses AI to evaluate NGS data is called ExploreSeq. And then we also have our phage display platform, which is called SpeedPlay. And you can see from some of these numbers here that we're evaluating a large repertoire to identify diversity. And then also I have some cartoons here that show which of these platforms highly leverages artificial intelligence. So both our single B-cell screening and our NGS evaluation really leverages AI data at an early stage. So we do a lot of in silico screening up front. These sequences are evaluated by our AI platforms, so then we can express a smaller number of molecules. So you can see here the number of molecules that are expressed. 73 coming from our single B-cell screening, 72 from our NGS. And these numbers are a little bit smaller, I would say, than traditional strategies, and that's intentional. Our goal here is to in silico screen all of the sequences up front so we can be very selective in the molecules that we move into expression. And the reason we can leverage this is because these molecules are pre-screened for developability, a whole host of factors from our AI platforms. So we can be selective in the number of molecules that we express. And then also I'd like to highlight the wet lab data that validates that these molecules are in fact binders. So in this specific case from the single B cell, you can see that 50 of the antibodies, 50 of the 73 that were expressed are bona fide validated binders. And then even better for the Explore-seq coming from NGS, 68 out of 72. So we have a very high hit rate, so we can leverage that and express just a subset of molecules and save resources and time. But this is where it gets interesting. So we take all of the wet lab data from round one. We can take that wet lab data, feed it back into our AI algorithm, and amplify those hits after we've fine-tuned our AI algorithm. So we take that data, feed it back into the AI platform, and do our bulk NGS and evaluate millions of sequences. And we get a second round of molecules. So all those millions of sequences from the NGS data are ranked by the AI platform. And we take the top 1,000 or so antibodies and move those into our other AI platform for developability. Those 1,000 antibodies are evaluated for developability by our XtalDev platform. And this is a proactive way of de-risking these molecules. So in the end of this process, we had 86 antibodies that were highly developable. 20 came from round one, and then 66 came from that second round after AI fine-tuning. And all of these CDRs are very diverse molecules. And at this stage, we take those 86 highly developable, pre-screened, and validated antibodies, and it moves into our XtalFold structure modeling platform. And this is all done in one day. So the XtalFold structure prediction is done in one day. So we take all of those 86 molecules, and then we can get structure of those molecules. And that can enable downstream engineering. And I'm going to talk a little bit more about XtalFold in the next few slides. But first, I just want to jump back into our hit selection. So smart fluidics, almost 70% of the molecules that are suggested by the AI platform are validated hits. So as I said, we're able to leverage that and really decrease the amount of resources and the protein that we actually have to make. For Explore-seq, the number is almost 100% coming from the NGS data. And all of these molecules have a range of affinities. And as I said, they're pre-screened for developability, so they don't have any obvious PTM issues, and they are highly expressible, highly thermostable. And that's what I'm going to talk about here a little bit. So the developability piece. Thousands of antibodies that are pre-screened by our AI platform, XtalDev, are ranked, and we're able to select just the top molecules from that AI prediction. And this is the wet lab data validating our in silico results. So there are 7 different metrics that we've validated here for hydrophobicity, thermostability, self-interaction, and polyreactivity. We just selected a subset of molecules from the 86 developable binders to just show and validate that we're seeing high-quality molecules that are coming out of our in silico screen. And then also it's important for us to have a wide range of diverse CDR sequences, and our AI algorithm is intentionally selecting those types of molecules. And then oftentimes a project will come to us and the project knows specifically what epitope they want to identify, and we can use our AI algorithm to identify binders to a specific epitope. But we can also go for diversity if the project requires that. And in this specific case, the project was looking for a diverse set of epitopes. And in this case, we identified 11 unique epitopes. And we use our XtalFold structure prediction algorithm to confirm those epitopes. And that's what I'm going to talk about a little bit more now here in the second case study. So this second case study uses our structure prediction algorithm to do engineering tasks downstream. I'm going to focus on superhumanization and pH-sensitive binding. So you can imagine what you would do with a predicted structure, a predicted complex of your antibody and antigen at a very early stage. So with sequence information alone, we can predict the structure and use that for engineering tasks. Now, there are a lot of different tasks that you can do if you have the predicted structure. Today, I'm just going to focus on two of those: pH-sensitive engineering and superhumanization. So again, this is a bona fide case study where we took 36 antibodies and generated the predicted complex structure of those 36 antibodies. And we did our high throughput epitope mapping using XtalFold. That data is moved into our in silico epitope selection process. We select antibodies that have the ideal binding characteristics and then also confirm that they're functional to move into our pH sensitivity optimization process. And in parallel, we superhumanize the antibody. So we know what contact residues are present in this antibody, and we can avoid those contact residues, and the non-paratope binding residues can be humanized in our process of superhumanization. And all this can be done in parallel to get our lead molecule. So just to back up a little bit, XtalFold is our structure prediction algorithm. I don't have a lot of time to go into all the details, but we do have a poster that goes into this specific process and highlights our XtalFold platform. And I'll also be at our booth later if you guys want to talk a little bit more about XtalFold. So this is probably our most exciting AI platform right now. It's a world-leading protein complex prediction algorithm. So from sequence information alone, sequence of your antibody, and sequence of the antigen, you can get complex of 100 or so structures in one day. And this is our own validated wet lab data that shows that our XtalFold platform is very effective at getting an accurate structure. All of this data here is the DocQ scores. Anything on the right is good, the left is bad, and they're very similar to the PDB structures that you can see. So very comparable to other platforms that are out there right now, and I'd love to talk more about XtalFold. But a little bit more about how we use these structures after we generate them. So for pH-sensitive engineering, not all antibodies are amenable to pH-sensitive engineering. So we took those 36 antibodies, determined epitope, and then identify an antibody that has binding to a negatively charged patch, so we could introduce histidines into the antibody and potentially get pH-sensitive binding. We select that parental antibody and confirm that that molecule has the desired activity. So it's both functional and hits the proper epitope that is amenable for pH sensitivity engineering. And this is some of the details from that process. One of the benefits we have of having the predicted structure at an early stage is we can focus on a subset of the CDR residues so that we can build a comprehensive yeast library of histidine mutants. I don't have too much time to go into the details, but we were able to build that library by focusing on a subset of those CDRs. And then, as I said, in parallel, we're also doing superhumanization. So we can identify the contact residues and the non-contact residues, and then humanize those non-contact residues in parallel, so that we can get a fully human scaffold of those non-paratope residues. And this kind of summarizes all of that work. So we originally had a chimeric parental antibody. That molecule was superhumanized and retained binding. And then also we were able to introduce pH sensitivity. In this specific case, there were two key histidine mutations that conferred pH sensitivity. So in summary, I was able to show you two different case studies focusing on hit generation and engineering. Now, AI is more useful in some cases than others. We have extensive experience in identifying which of those use cases are best suited for AI. I personally don't think that at this time, AI is going to replace any of the wet lab work that we do, and I think that's one of the luxuries we have, that we have the wet lab and the dry lab working in conjunction. So today I was able to go through a few of our impactful AI platforms, but we have a whole host of AI algorithms that we use to accelerate and enable antibody discovery. I'd be happy to talk more about it at our booth, and we also have a poster covering XtalFold. So thank you so much for your time.